welcome to operating systems. Right. So last time we were talking about synchronization of a different type. So far we had talked about locks which give mutual exclusion. Now we were talking about synchronization of a different type where somebody may need to wait on a condition to become true, and when that condition becomes true by another thread, then that thread may need to signal the other thread that the condition has become true, so it can wait, right? And so we said, we were looking at this example of a producer consumer where there's one thread which is producing. In our example, it was a network thread, and then there is one thread which is consuming. In our example, it was a server thread, right? So let me just say producer, consumer, example. Okay, and the way we wanted it to work was, let's say if this is the producer and this is the consumer, right? Last time I called them the network and the server threads, but let's just call them in their generic names today, producer and consumer. And let's say there is a queue, right? So let's say it's a queue of characters. So it's a buffer, char queue, max size. Right? So it's an array of max elements which are our characters. Producer is going to produce an element into max, and consumer is going to consume an element from max, right? Apart from this, there's another variable called count, which basically says how many elements there are in the queue. Okay, so plus it's not just enough to say count. It's actually, so what we're going to do is let me use a different sheet here. So let's say what I'm going to do is, let's say this is my queue. This is element 0, this is element max minus 1. Right? So, and there are two threads, producer and consumer. What the producer will do is producer will control a pointer, so which will be the tail, and the consumer will control a pointer called head. Okay, the producer will push an element here. So when a producer says produce, then tail will move one element to the right, and an element will be produced. Right? So, and similarly, consumer, if it wants to consume an element, it will just move one element to the right, and this element will be consumed. Right? So producer will keep moving the tail, consumer will keep moving the head, right? And all the elements between the tail and the head form the current size of the buffer, right? Okay. Also, if head becomes equal to tail, what does that mean? It means that the buffer is empty, right? So if head is equal to tail and the consumer wants to consume something, then what should it do? It should wait, because there is no element that can be consumed, right? Right. So only if head is strictly less than tail can the consumer consume an element. Similarly, the queue is limited size, right? So if the tail becomes equal to max minus 1 and the producer wants to produce an element, what should happen? Well, if you want to use the entire space, the right thing to do is roll back the tail to 0, right? Assuming head is greater than 0, you can produce the next element here, right? So it's possible So what? Let's see. So so consumer action is, consumer does what? It basically says Q tail, sorry, Q return value is equal to Q head, right? And head is incremented by 1. That's the logic of a consumer, and it will just return ret. Right? So the value that was consumed is returned by the consumer, right? And what is the code of the producer? The code of the producer is, so he wants to produce an element E, right? So what he'll do is he'll say Q tail is equal to E, all right, and tail is equal to tail plus 1, right? So roughly speaking, producer returns the value at the current pointer of head and returns in ret and increments head, and producer produces an element at the current value of tail and increments tail. Of course, so now instead of count in this example, I will have 2 pointers called head and tail. Okay, and initially both head and tail will be initialized to 0, let's say, right? Okay, and at that time the queue is empty. Of course, this code is not complete, because the consumer cannot just consume an element, it should check whether the element that it's trying to consume is actually valid. And how can it check if the element it's trying to consume is valid? Well, head, in this example, an element is valid if head is strictly less than tail, right? On the other hand, it's possible for the tail to get wrapped around, right? So tail can come here, in which case head may not be strictly less than tail, but head should never be equal to tail, right? So one way to check if the queue is empty is that if head is not equal to tail, that basically means that the element in the queue is available, is valid, right? Else, just say error. Right? So that's the consumer code. You basically just increment head. You first check if head is equal to tail. If head is not equal to tail, only then you can consume. If head is equal to tail, you are trying to consume from an empty queue, right? In which case you return an error. All right. So also, once again, this code is not completely correct, because I can't just increment head, right? Because if I just keep incrementing head, head will just run away and become greater than max. So what I need to do is I need to roll it back. So I say head is equal to head plus 1 modulo max. So basically means that if a head becomes max minus 1 is max minus 1, and you increment by 1, then it becomes 0, right? So it becomes a circular buffer. So this is nothing but a circular buffer. Okay. Similarly, what will the producer need to do? The producer cannot just produce an element. It first needs to check whether there is space in the queue to produce an element. How does it know whether there is space to produce an element? Let's see what will happen if the queue becomes full. If the queue becomes full, tail will keep, let's say producer keeps producing elements and consumer is not consuming elements. So tail will keep incrementing, right? Then tail will wrap around. Then tail will again keep incrementing until tail becomes equal to head, right? So at the point when tail is equal to head minus 1, you can say that the queue is not full. But if tail is equal to head minus 1, then the queue is full, right? So what you can check here is if tail is not equal to head minus 1, and you know, once again this head minus 1 is not a strict head minus 1, you should also do it, you know, modulo max. So if head is equal to 0, then minus 1 modulo max will become minus max minus 1, let's say. Then you will do q tail is equal to e, tail is equal to tail plus 1, else you'll say error. Okay? Because producing to full queue. Right? In this case there was an error because consuming from empty queue. Right? Okay. So that's producer, that's consumer. And here I'm really talking about producer consumer within a single thread. So only one thread is going on, and it's a responsibility of the programmer to make sure that it never consumes from an empty queue and it never produces to a full queue. Right? But now I want to talk about a situation where there's a queue, one thread is calling consume, another thread is calling produce, right? And if the queue is full, then produce should not return an error, it should just wait for the queue to become not full, right? Similarly, if the queue is empty, then the consumer should not return an error, it should just wait for the queue to become non-empty, right? Okay. So what I'm going to do is one thread is going to act as a consumer and another thread is going to act as a producer, and instead of returning errors, they will just wait for this condition to become true, right? So let's say one thread will become consumer and then a thread will become producer. Of course there is this queue where all this is happening, and the logic is that if the queue is full, then wait. If the queue is full, if the queue is empty, then the consumer should wait, right? And wait till when? Right? Wait till the queue becomes not empty. And who will tell him whether the queue has become not empty? The producer should tell the consumer whenever it adds an element to an empty queue, right? So there should be a notify consumer if not empty. Right? In fact, notify consumer if you transition from empty to not empty, right? So let me just write it clearly. Notify on empty to not empty. Similarly, consumer needs to notify on full to not full. Okay. So if the queue was empty and the producer made it not empty, then the consumer needs to be notified. If the queue was full and the consumer made it not full, then the producer needs to be notified, right? And because they may be waiting for these conditions to become true, not empty or not true, not full. So now the question is, how does one write such code? And we saw one real example of when this may be needed. There's one thread which is implementing the network, that is acting as the producer. There's another thread that's acting as the consumer, that's the server. And there's a queue in the middle. This queue can be implemented as a circular buffer. And but the semantics should be that if the queue is empty, then the server should wait. And if the queue is full, then the network should wait, right? So it's the same thing. I'm just generalizing it to a general producer consumer problem. Okay, and this kind of a pattern is seen very clearly in different programs and different settings. Right. So now let's see how we are going to implement something like producer consumer. Firstly, just using locks is not enough, right? Because you need these special ways to wait and notify, right? And locks don't give you, acquire and release don't give you any way to wait. They only wait if the lock is not taken, but it's not possible to check a condition and then say release the lock if the condition is true. So locks only do mutual exclusion, they can't do this wait and notify that we want in this producer consumer example. So I'm going to define a new abstraction. So we have seen one abstraction called locks. We're going to see another abstraction today called condition variables. And I'm going to implement producer consumer using condition variables. Right? So let's define what are condition variables. There's a type, let's say CV, condition variable, and then there are two functions. Void wait on struct CV star and struct lock star. All right. Okay, I'm going to explain what these are, and then there's another function called notify struct CV star. So these are, so this is the abstraction of condition variables. Yeah, just ignore this line. Right. So the abstraction is there's a type, just like there was a type for lock. So there's a type for condition variable CV. There's a function called wait, which waits on this condition variable. Okay. And there's a lock which I'm going to explain very soon. But let's say, let's ignore the lock for a minute, and let's just say we wait on this condition variable. Right. And then there is a function called notify, which says notify all threads that are waiting on this condition variable. So any thread which is waiting on this condition variable will get woken up when somebody calls notify on that condition variable. Okay. So one thread can call wait on the condition variable, another thread can call notify on that condition variable, and in fact multiple threads can call wait on the same condition variable. If a thread calls notify on that condition variable, then all threads that had called wait on that condition variable will get woken up. If there was no thread that had called wait on that condition variable, then notify will have no effect, right? Okay. So an analogy can be that there's a telephone number. All right, that telephone number is your condition variable, let's say, right? And you basically say, you want to go to sleep, and so you basically, let's say I have a job, and my job is basically to listen to the next telephone call, right? Now each time, so what will happen is, let's say there's a telephone device, and there are lots of calls that are coming in, right? If lots of calls are coming in, the telephone will have, has a log which basically stores all these calls. So it has some buffer where it will store all the calls. So my job is, take one call, each call is a request. So I take one call and I perform an action based on that call. Sometimes it may happen that there are calls, right? Let's say it's in the middle of the night, I look at the telephone and I say, oh, there are no more calls now. So I say, oh, good, I can go to sleep. I can get some rest, right? So I go to sleep. But should I go to sleep forever? No. I say I go to sleep on this telephone number, right? What that means is that I will keep sleeping till somebody makes a call on this telephone number, right? So going to sleep is like saying wait on this telephone number or wait on this condition variable, and making a telephone call is like saying notify. So somebody makes a telephone call on this number, then I'll wake up, all right? And then I'll retry my job, which is to check if the buffer has some request or not, right? So that's basically the analogy. One thread can go to sleep on a condition variable. A condition variable is nothing but a data, an address or a telephone number, if you will, and notify is basically making a call on that telephone number so that anybody who was waiting on that telephone wakes up. And then when he wakes up, he can, retry whatever he wanted to do. Of course, he went to sleep because, there was some condition that was false. The condition in this case was that the queue was empty, right? So the queue was empty, so I said, oh, the queue is empty, let me take some rest. Right? Now, if somebody is making a call to that telephone number, it basically means that he has some reason to believe that the queue is not empty now. For example, he may have added some request to the telephone and said, oh, if you're sleeping, please wake up. Right? So that's basically the analogy. One thread can call wait on a condition variable, which means it will go to sleep till somebody calls notify on this condition variable. And a thread which calls notify on the condition variable has the effect of waking everybody who was waiting on that condition variable. Right. Now, what's the meaning of this lock? All right. So the semantics are that you must be holding a lock before you call wait. All right. But when you call wait and before you go to sleep, you will release this lock atomically. Right. So it's like saying this. So let's say, let's take the same example. I have a job and I'm attending to calls on this telephone. And let's say I checked my telephone buffer and I said, oh, there are no jobs for me, and I'm about to go to sleep. Now there is some time lag between checking that there are no jobs and actually going to sleep on that telephone number. Right? Now between this gap, right, between this gap of checking and going to sleep, if somebody makes a request and calls the telephone, I will miss it because I haven't yet slept on that telephone number, but I have decided that I'm going to sleep. So I'm preparing my bed and I'm about to sleep. I have put earplugs in my ears so that nobody, I cannot hear anything. And only when I go to sleep am I going to remove my earplugs and I'm going to start hearing telephone calls. Right? So while I'm doing that, if a call comes, it will get lost. Right? So this is a lost notify problem. So somebody makes a notify, it will get lost. And so, I will not be, and then I go to sleep, then what will happen is I'll keep sleeping forever because the person who was supposed to wake me up has already made a call and he thinks that I should have been woken up, but I actually haven't woken up because of this race condition. Right? The race condition is I checked that the buffer is empty and I have decided that I'm going to sleep, but before I slept, somebody made a call which I missed. If he had made a call after I had slept, I would have got it because I would have slept with the telephone close to my ears. But if if he made the call before I slept, then that telephone call can get missed. All right. So what does the lock help? How does the lock help in doing this? The lock basically says that once before you check the condition and you go to sleep, you should acquire a lock. So in some sense, let's say this is a room, I acquire a lock on this buffer. So I say, I'm going to decide what to do, but till I don't sleep, nobody else is allowed to touch this buffer. So in that way, this mechanism of checking the buffer and going to sleep will become atomic. Right? So if I check the buffer and I see that it's empty, I'm still holding the lock. So nobody can actually add to that buffer till I'm holding that lock. And now I'll go to sleep, and only after I've gone to sleep will I release the lock. Right? So I'll hold a lock, I'll check the telephone buffer, and then I'll say, okay, with the lock I'm going to go to sleep, but my sleep operation will basically ensure that as soon as I have slept and I have the telephone close to my ear, I will release the lock. Right? Now, it's only now because I've released the lock can somebody add to that buffer, because till I'm holding the lock, nobody else can touch the buffer. Right? So I'll release the lock, now somebody can touch the buffer, now he can make notify, but because now I already have the telephone close to my ears, if he makes a notify call, I'll wake up. Right? Also, when I wake up, the semantics are that when you wake up, before you actually do anything, the first thing you will do is you will reacquire the lock. You will try to reacquire the lock. Right? So that whatever you do next, you will have the lock with it, right? So the semantics of wait are that before going to sleep on this condition variable, you will acquire the lock atomically. Sorry, so you must have acquired the lock before going to wait. When you call wait, this lock gets released after you have slept in an atomic way. Also, when you wake up, this lock gets reacquired in an atomic way, right? To avoid the problems of lost notify. Okay, so let's see how it's used to make things clearer. Right. So I'm going to use the producer consumer example to demonstrate how this is used. Okay. So the one way to do this is basically, let's say this is the producer and it wants to produce an element E. Right. So what I'm going to do is I'm going to have a lock. So there is a Q, there is head, there is tail, and there is a lock now. Right. These are global variables. Okay. Let's also say that there are two condition variables. One is not full. These are CVs, and not empty. Okay. So what the producer is going to do is it's going to take the lock. So it's going to say acquire lock. This lock is basically acquiring the lock on the Q, right? So it's, you know, it's, let's call it Q lock. So it's Q lock. Acquire the Q's lock, right? Then check if head is equal to tail plus 1 mod max. What does this mean? Head is equal to tail plus 1 mod max. What does this mean? That the Q is full, right? This basically means Q is full. I'm trying to produce when the Q is full, so what should I do? I should wait. And I should wait on what condition variable? I should wait on not full. And the lock I'll give is Q lock. Okay. So let me just use ampersand to say that this is the address of Q lock. Okay. Else, I'll just do what I used to do, which is basically Q tail is equal to E tail plus plus, right? And release Q lock. Okay. Let's look at this code. So what am I saying? I'm saying I want to produce an element into Q. And so before I do that, because Q is a shared variable, let me acquire the lock for mutual exclusion. But then I also want to check whether the Q is full. If the Q is full, then I'll wait on this condition variable that I've called not full, which is basically means that I'll wait for the Q to become not full. But it's just a name. I could have named it anything else, but it's a suggestive name. So I say wait on this condition variable called not full. and release the lock after you have made it not full. I need to release the lock because any consumer will also need to acquire the lock, right? So anybody who will make it not full needs to acquire the lock. So the semantics are that it will release the lock and it will start waiting on this condition variable. If another variable, another thread calls notify, then this lock will get reacquired, right? So let's look at this. So this, the effect of this is that it will start waiting on this condition variable, and it will also release the lock. When it gets woken up, it will reacquire the lock, or it will try to reacquire the lock, and only then it will come to this statement. At this point, it will definitely have the lock, because if this was not true, then still it has the lock. If this was true, then it would have released and reacquired the lock. So at this point, the lock is held. Right? And because the lock is held, you can do this operation. You are also sure that Q is not empty at this time. Q is not full. Right? So this check here makes sure that by the time you are here, Q lock will be held and Q will not be full. And so you can now produce an element and then release the Q lock. Okay. So now question is, how will the consumer notify? Right. So let's look at the notify code for the consumer. Let's say this consumer, right? Consumer just return an element, and once again it's going to acquire Q lock, right? And it's going to check if the queue is empty, right? So if head is equal to tail, which means the queue is empty, right? Then what will you do? Wait on another condition variable called not empty, and once again you will release the Q lock. Okay, and then I'll say Q, so let's say return ret is equal to Q head is equal to head plus 1 modulo max, right? Release, right? But also, what should I do? I should check, or I should probably notify not full. And then release Q lock. Right? So what have I done here? This statement is the important statement. I'm saying I've just consumed an element, right? And so definitely the queue is not full at this point. And so any thread which was waiting on this condition variable called not full can be woken up, right? So any thread which was waiting for the queue to become not full can be woken up. And so that's why you call notify. And so if there was a thread which was waiting here, it will get woken up. And the first thing it will try to do is to acquire the Q lock, right? Similarly, if the consumer was waiting for the thread to become not empty, who is going to wake it up? Who is going to notify it? It's the producer which needs to notify it. And so this code is incomplete. Actually, you should write here notify what? Right, so let me write it a little bigger. Firstly, this tail plus plus should be tail is equal to tail plus 1 mod max, right? And this here should be notify what? Notify anybody who is waiting for the queue to become not empty. I've just produced an element, and so the queue is not empty. If there's a consumer that's waiting for it to become not empty, you can wake it up. Okay. So this notify will wake up the consumer which is waiting on this wait. Similarly, notify will wake up the consumer, will wake up the producer which is waiting on this wait. Right? Why? Because the condition variable here and the condition variable here have the same name. Similarly, the condition variable here and the condition variable here have the same name. Right? So this is going to notify this and this is going to notify this. Also, we have, the way we have structured the code, we have make sure that when we notify somebody, it's sure that the condition that he was waiting on is true, right? So when you notify the consumer, you're sure that the queue is not empty because you just produce an element, right? So the consumer can wake up and it will find the queue not empty, and it will be safe for him to consume an element here. Similarly, when the consumer notifies somebody, not the producer can be sure that the queue is not full and it can produce an element because the consumer has just made some space, right? He has incremented head, so the tail cannot be equal to head cannot be equal to tail plus 1. It has to be at least head tail plus 2 or something bigger. All right. Okay. Let me open the floor for questions at this point. Any questions? Okay, I have a question for you. Do I need to call notify every time I consume? All right. So there's a question from LNMIT that what is the code for notify and wait? Let's hold on. I mean, how is notify and wait implemented? There are many ways to implement notify and wait. It depends on at what level you are implementing it. I have already discussed how to implement locks. Notify and wait are implemented internally using, but we'll see if we can do it in the limited time we have. But let's understand the meaning of notify and wait before we look at the implementation of notify and wait. Let's assume that these are atomic, completely atomic. Notify is atomic, wait is atomic. Right? What does it mean for wait to be atomic? Basically, the release of the lock and the act of going to sleep are atomic with respect to each other, which means nobody can come in the middle and change things. Right? Okay. Any other question? All right, I have a question. Do I need to call notify every time I consume? Right? So what will happen? Each time I consume something, I'll call notify. Does it make sense to call notify every time? Or can I reduce the number of calls to notify? So somebody answer this question. Do I need to call notify every time I consume? All right, so LNMIT says no. Okay, can I talk to LNMIT? All right, so hello LNMIT, please tell, please say.
Hello, sir.
Please
We need to call notify only when. Can you show the code once again?
Yeah, please show the code. Okay.
Yeah, so we will call notify only when the sorry, the producer thread is waiting.
Okay. And how will I know whether the producer thread could be waiting?
Uh, by checking. One second.
Audio.
Hello.
Hello. Yeah. So there's some problem at the audio in your side, I think. Okay, go ahead.
Hello.
Hello.
Yeah. So
Yeah, it's clear now. Yes, please say.
so we, I'll type the answer.
You will type the answer. Okay. Let me ask another question. All right, you just need to say yes and no. Okay. So yeah, just hold on. So just say yes or no. So firstly, if I call notify extra number of times, is it incorrect?
No.
So firstly, I can call notify any number of times. It doesn't matter. If there was somebody who was waiting on it, it's okay. If nobody is waiting on it, it doesn't matter, right? So it's okay. This code is correct, but you can reduce the number of notify calls because as you said, if there is no producer waiting on it, then why to call notify? And if I can determine that definitely no producer is waiting, then I don't need to call notify. And one way to know this is assuming that there is only one producer and one consumer. If the buffer was already full or already already not empty, right? So let's say the buffer already had 5 elements in it, and hold on. So let's say the buffer was already not full, right? So let's say the maximum size of the buffer is 100 elements, and I have only the buffer when I consumed had only 75 elements. So if it had 75 elements, clearly the producer must not be waiting, right? Because there's already space. So there is not unlikely that a producer will be waiting. A producer will be waiting only when when I consumed the buffer length was 100, right? So I made it from 100 to 99. That's the point where it's possible that the producer could have been waiting. Even there, it's not necessary that the producer was waiting, but it's possible that a producer was waiting, and only then I need to call notify. If I made the buffer from 75 to 74, there is no need to call notify because I'm sure that the producer is not waiting, right? So I can check here if so head is so I'm incrementing head. So if the previous head, so I can say that if the head was basically just equal to tail minus 1, right? Or so if all right, so if tail plus 1 was equal to head minus 1, right? Which means the queue was full before this, then call notify, right? And this tail plus 1 and head minus 1 should be interpreted in a circular way. So when tail plus 1 means if tail was equal to max, then tail plus 1 is equal to 0, right? If tail was equal to max minus 1. Similarly, head minus 1 is if head was equal to 0, then minus 1 becomes max minus 1. So if the queue was just full just before I consumed an element, only then I need to call notify, because it's only then that it's possible that a producer could be waiting. Okay. Similarly, here in the producer, I don't need to call notify every time. I only need to call notify if the queue was empty before I produced, right? Calling notify every time, I can have here if what? If if tail plus 1 or sorry, if head plus 1 is equal to tail. Okay. So there's only one element in the queue. So if there's only one element in the queue, and once again head plus 1 should be interpreted in a modulus way, in a circular way, only then call not empty, right? So you call notify. So in other words, notify not empty if queue has one element after produce, right? And similarly notify not full if queue has max minus one elements after consuming, right? Only then you need to call notify. Other cases you are just wasting your time by calling notify. Okay. All right. So any questions at this point? Okay. If there are no questions, okay, there's a question from VCE. Yes, please.
Hello.
Yes, yes.
Hello.
Yeah. Yes, please. Please ask a question.
First we have notified the producer like our consumer, and then we have released the lock. Is there any adverse effect if we first release the lock and then notify?
Okay. Very good. So the question is, we have notified before releasing the lock. Is there any advantage of releasing the lock before notify? This is, so the question is really this. Let's see. In this slide, could the notify have happened after the release? Okay. Right. So, all right. So the question is, do we have to necessarily notify before releasing the lock, or can we notify after releasing the lock? Okay, interesting question. Let's see if we notify after releasing the lock, what can so I'll answer this question, but before that, actually, I'm going to show you that this code is actually not completely correct. All right, and then we are going to discuss whether we can actually swap notify and release. Okay, so let's hold that question for that now. It's a very good question, and we'll come to it either in this lecture or the next lecture. But actually, I'm going to show you that this code is not completely correct if there are multiple if there are multiple consumers, so or multiple producers. So if there is only one producer and one consumer, it's okay to swap these statements. It's okay to release the lock and then notify. Okay. But if there are multiple consumers and multiple producers, then one has to be careful, and we're going to, and then this code is actually not correct, and we're going to look at it in a short while. There's another question from LNMIT. After I notify, why do I need to reacquire the lock? Why does the thread which was waiting need to reacquire the lock? Right? The answer is, well, that's the nature of the abstraction, that it will reacquire the lock. And if you see, it's very important that it reacquires the lock, because if it doesn't reacquire the lock and then it comes here, then it will get confused, because it cannot just start operating on the queue. Right? You may have to put an acquire queue lock yourself somewhere here, which you would want to avoid. Right? So the abstraction is, because typically when you come out of wait, because wait released the lock. So when you woke up, then you would want to reacquire the lock, right? So it's just an abstraction. If wait was not reacquiring the lock, in most cases you would want to reacquire the lock yourself, right? So it's better for the abstraction itself to say that it will release the lock before sleeping and it will reacquire the lock as soon as it wakes up. Okay. All right. Now let's look at what happens. So to answer this question whether notify and release can be swapped, let's first look at what can happen if there are multiple consumers and multiple producers, right? So what do I mean by multiple producers and multiple consumers? Let's say there are multiple threads, and let's say these are consumers and these are producers. And I'm just drawing two, but there could be multiple. There could be 3 consumers and 2 producers or whatever. Right? So far I was looking at the case where there was 1 producer and 1 consumer, right? The network thread was the producer, the server thread was the consumer. But it's possible that there is one producer and multiple consumers. For example, each CPU could run the server thread separately on the same queue. Similarly, it's possible that there are multiple producers because there could be multiple network cards and they're all adding to the same queue, right? So there could be multiple network threads for the different, so one machine could have multiple network ports and each port is served by a different thread and they want to use the same queue, so there can be multiple producers and multiple consumers. Now let's see if this code that we wrote, is it correct if there are multiple producers and multiple consumers. Okay. So what will happen? Firstly, there's a lock. So if multiple consumers try to come into this this area, this is a critical section, only one of them will be able to acquire the lock. Others will get blocked here, right? So let's say initially the queue was let's say initially the queue was empty, right? Now two producers come, two consumers come, one consumer gets blocked here, the other consumer checks that the queue is empty and goes to wait, right? So let's say there are 2 consumers. First, let's say queue is empty. Consumer 1, let's call it C1, checks and waits, releasing the lock. Okay. Then the producer, let's say there's a producer P, and let's say there's just one producer. I can generalize it to multiple producers, but let's say there's just one producer. Producer produces, and notifies. Notifies what? It doesn't notify someone, right? It notifies not empty. Right? What's the next thing that could, what are the next few things that can happen? It's possible that C1 wakes up from the wait call. It will. But the first thing it will try to do is it will try to acquire the lock. Right? Now before C1 acquires the lock, C2 comes, enters, calls consume and acquires lock. Before C1. It's possible. C1 was waiting, P called notify, C1 woke up, and as soon as it woke up it wanted to acquire the lock, but before it could acquire the lock, C2 comes along and acquires the lock. Right? So C1 wait. So C2 has already and will it need to wait? No, it just consumes because the buffer is not empty. The producer has just produced an element, so C2 will consume it, right? And now C1 consumes and releases lock, right? And then C1 acquires lock, right? But now it will not check, right? Because if you look at this code here, it was waiting here, it has been notified, it acquires the lock, and now it just goes on and tries to consume. It doesn't check again, right? So what it will do is it will acquire the lock and tries to consume from empty buffer, from empty queue. Error. Okay. So this code is actually not correct if there are multiple consumers. It's also not correct for a similar reason if there are multiple producers. So I have given you an example where the queue was empty. One consumer started waiting for the queue to become not empty. But before it could wake up, another thread came in and changed the queue to back to empty. And now this consumer tries to consume from an empty queue. Similarly, multiple producers could come in. One producer could start waiting on the queue to become not full. A consumer may consume an element, the queue will become not full, but immediately after it releases the lock, another producer can come, make the queue full, and now this older producer can now again try to produce into a full queue, right? So same thing, it's symmetric, completely symmetric. So consumer can consume from an empty queue in this code if there are multiple consumers, and a producer can produce to a full queue if there are multiple producers. So this code is actually not correct in the presence of multiple producers and multiple consumers. What was needed? What was needed was that after he came out of wait, he checks again. Right? It's like saying I have slept. I have the phone call. I have the telephone, and I'm going to. Then the phone rings. As soon as the phone rings, I wake up. When I wake up, I get the lock. I cannot assume that the phone definitely has a buffer or has some element in the buffer. I should check again whether the element there's an element in the buffer or not. Right? And so I should check again after coming out of wait. Right? And one way to do that is to replace this if with a while condition. Okay? So after you come out of wait and you reacquire the lock, you'll go and again check whether head is equal to tail or not. And if it is, then you'll again go to wait. And if it's not, only then you will come out here. Right? Notice that this check that you're doing with head is equal to tail is always being done with the lock held. So there are no race conditions here. Okay? Similarly, in the let's see. Where is my code for the producer? Okay, so similarly in the producer code, I can replace this while if with a while, and this code becomes correct even in the presence of multiple users and multiple consumers. So basically, as soon as you come out of wait and you reacquire the lock, you will want to check the condition again, right? So you want to do the same thing again, because it's possible that before you got the lock, somebody else changed the state. Somebody else got the lock and changed the state. So you should check again. Okay. Similarly, now let's say you have multiple producers and multiple consumers. Recall that I said that notify wakes up all the people who are waiting on that particular condition variable. So it's possible that multiple people are sleeping on the same telephone number, and if somebody makes a call on the telephone number, all of them will wake up, and only one of them will be able to acquire the lock. Others will have to wait for that thread to release the lock. each time he acquires the lock, he should recheck the condition, right? Because let's say there are 5 people who are trying to consume, all of them find that the queue is empty, all of them go to sleep. Now somebody produces one element, what will happen is all 5 will get woken up, all 5 should now try to acquire the lock, only one of them will get the lock. The one who gets the lock will check that the queue is not empty now, and he will consume the element. But after he has consumed the element, the queue is empty now. Now the other 4 consumers, when they will check, when they will acquire the lock and when they will check, they will again find the queue to be empty and they will again go to sleep. Right? So what will happen is, if there are 10 people who are waiting, there's a phone call that comes, all 10 wake up, only one proceeds, the other 9 just go to sleep again. Right? So it's sort of a race, who gets the lock first, right? But because lock, the acquire function itself is atomic, there's no problem. Somebody will get the lock first, but whoever gets it, the code is correct. Okay. All right. So I'm going to continue this discussion. I want to also discuss your nice question on whether notify can be put before or after the lock or not next time. But I would highly recommend that you look at this code, and in fact, I would recommend that you implement a producer and consumer scenario yourself using pthreads, POSIX threads on C, right? So it's very simple. Just you need to write this code. You need to declare a circular buffer, and you need to implement a producer and a thread and a consumer thread, and see how they play out. First, implement a single producer, single consumer with an if condition. See that it works. Then implement multiple producer, multiple consumer with an if condition, and see that it actually can fail. Then you replace if with while and see that it works again. All right. So I'll highly recommend that you do it yourself, and you will get a lot of experience in parallel programming. Okay. Right. So we are out of time. So please please do these exercises till the next week, Monday, and also let me know if you have any questions next time. So save your questions for the next lecture. Okay. Thanks.